All right, here we are in chapter 15. It's basically thermodynamics light. It's like diet thermodynamics. It's not quite thermodynamics, it's just like a mini version of it. All right, let's get into that. So, first section here is going to be talking about energy. So, what the heck is energy? Ponder, and I'll spit out the textbook definition here. All right, the textbook definition of energy is it's the ability to do work or transfer heat. So energy that's used to move something, we call that work. And energy used to change the temperature of an object, we call that heat. All right, so in physics, when you take that class, you'll learn that, come on thing, click, work equals force times distance. All right, work, it's force times distance. And so it's the distance over which the force is exerted. So if I'm like moving a box, right, I'm just going to draw with my little mouse pointer here. Let's say I want to get my box from here to here. I can either pick it straight up or I could slide it up this magical frictionless ramp. You might think, oh, I'm going to slide up the ramp. That's easier. You end up doing the same amount of work, right? If I pick it straight up, I use a large force over a little distance. If I slide it up a ramp, I'm going to do a small force over a greater distance, but you end up doing the same amount of work. Anyhow, I'm veering off into wacky land, but that's work. So force times distance is work. Let's get into heat. All right, so energy can also be transferred as heat. Heat will always flow from warm to cold. Always, guaranteed. All right, never the other way around, right? Unless you're making that happen. But on its own, heat will always flow from hot thing to cold thing, just like a marble will always roll down a hill, unless there's some outside thing messing around with it. Let's get to all this stuff. Let's click these things. These things are all animated. I just want to flip through them. All right, potential energy and kinetic energy. We talk about these a lot. Potential energy is energy due to position or composition. Gravitational potential energy is what you probably most normally think of when you think potential energy. If you go skiing or snowboarding or something and you get on top of the mountain, the lift brings you up to the tippy top, you have a lot of potential energy because you're on top of the mountain. And then you start sliding down that hill, and that potential energy is converted into kinetic energy, the energy of motion. Right. You've actually already seen a little bit of stuff on kinetic energy. It's 1/2 mv squared is the equation for it. And we talked about it also in terms of it's how we define temperature. So temperature is it's a measure of the average kinetic energy of the particle. So as we increase the temperature, the particles are moving around more and more and more. It might be just vibrating, but they're moving. Right? And then finally they pop totally free and you go to the gas state and all that crazy stuff. So you've seen some of this stuff before. All right, units of energy. Let's get to that. So the actual SI unit of energy is a joule, and it's kind of weird looking because you're like, okay, 1 joule is 1 kilogram meter squared per second squared, which does seem kind of odd. Like, those are some weird units, all right? But remember I just told you work equals force times distance. And when you take physics, another thing you'll learn is Newton's second law, and that's force equals mass times acceleration. So work actually equals mass times acceleration times distance, MAD. Work makes you mad. Now you have proof that work makes you mad. All right, but the unit of mass is a kilogram. Acceleration would be meters per second squared, and then distance is meters. And when you multiply all that stuff together, you get this crazy thing, which is a joule. Another unit that you may have seen and are very much more familiar with is a calorie. All right, a calorie is also a unit of energy. So when you look at your food and you look at the back label, the nutrition label, it lists calories. That's like the energy content of your food. Pretty cool. All right, how to convert. All right, so 1 calorie is 4.184 joules. Really important number. Have that thing written down or commit it to memory. That wouldn't hurt. All right, there's the law of conservation of energy. It says energy can be converted from one form to another, but it can neither be created nor destroyed. In other words, to say that is the total energy content of the universe is constant. Dun, dun, dun. This is also known as the first law of thermodynamics. All right, so the energy isn't created or destroyed. Cool. All right, there's some stuff we need to know here. Wow, there it is. Like, why did that not pop up? Who knows? All right, there's some definitions we need to know. So in thermodynamics, we have some really crazy definitions. So there's the system, there's the surroundings. So the system is the part of the universe that you want to pay attention to. The surroundings is everything else in the universe. I mean, it's literally talking the universe, like not just the classroom here, like the entire universe. So, for example, like if you had two aqueous solutions and you mix them together, and the things you care about would be the solutes. So those solutes that are floating around in there, those are your system, and they're all that you care about. The water, that's the surroundings. The beaker that it's in, that's the surroundings. The bench top, that's the surroundings. The busted up old car down the street, that's surroundings. Jupiter, Crab Nebula, Andromeda Galaxy, it's all surroundings. Like everything else in the universe is the surroundings. So in thermodynamics, system plus surroundings equals the entire universe. Cool. More stuff here. All right, this should be the last slide though once I get through it. Endothermic. You may have heard me say this before, but now here you go. Officially, endothermic. Thermic, think heat. Endo kind of sounds like into, and endothermic means heat flows into your system. So if heat is flowing into your system, that's an endothermic process or an endothermic reaction, kind of depending on what you're doing. So that means energy is absorbed from the surroundings. All right. If it's exothermic, that means energy flows out of your system. So it's like heat is exiting your system. So energy gained by the surroundings must be equal to the energy lost by the system, right? Because energy is not created or destroyed. So if your system absorbs heat, it got it from the surroundings, right? And vice versa. If your system gives up heat, it goes into the surroundings. All right. That's it for the first little chunk here.